So let's take a look at this document here I've prepared to understand reinforcement learning. And I want to describe a little bit about the history of GRPO, how we got there. And I want to talk a little bit about how GRPO works. So GRPO is Group Relative Policy Optimization. And what does it do? Well, ORPO, let me just briefly recap. I know I did this in the last video, but supervised fine-tuning, if you have a question like, is Paris the capital of France? You're trying to predict the next token. In the forward pass, you have a certain probability of yes, of maybe or no. The ground truth is yes. And so when you do the backward pass, you're going to update the probabilities to based on the difference with the ground truth. So after the back propagation, you're going to have something that looks a bit like maybe yes increases to 50%, maybe goes down to, let's say, 15%, and no goes down to 25%. And that's because you have a loss, because the ground truth value for yes is well above the forward pass value, and the maybe value is above what the ground truth value is. The ground truth value for maybe is 0, and for no, it's 0. So that's how things work within supervised fine-tuning. Now, when you look at ORPO, which is odds ratio preference optimization, the loss is more complicated. It has the cross-entropy loss, which is the difference between ground truth and forward pass. But it also has, adjusted by this hyperparameter beta, it has odds ratios. And the odds ratios reflect the ratios of the chosen answer versus the rejected answer. So I can give an example here of how ORPO works. Let's just copy what's happening here with ORPO. So you're going to have, is Paris the capital of France? And when you're predicting this, you're going to have the forward pass, you're going to have the chosen answer, which also will serve as ground truth for the cross-entropy term. And then you're going to have a rejected answer. This is not here in just supervised fine-tuning. And the rejected answer, for example, might be maybe, or let's say the rejected answer is no. So the rejected answer here is going to be no with, let's say, 100% probability. And it's going to be yes with 0%. Let me get this right. There we go. And maybe with 0%. So you've got forward pass. This is what the model actually predicts. But now in ORPO, you have not just a ground truth, you have a chosen answer and you have a rejected answer. Now, check here how the backward pass is a bit different, because the backward pass now is going to incorporate both cross-entropy term, plus it's going to incorporate the odds ratio term. So it is going to move the probabilities down in the same way supervised fine-tuning did to 50, 15, and 25. It is going to have that effect. But furthermore, it's going to have the effect of moving probabilities away from the rejected answer and towards the chosen answer. So in addition, it's also going to increase the yes answer. Let me write it out like this for clarity. So it'll be 40%. Then let's say it's plus 10% for the cross-entropy. But then there's going to be an additional 10% for the odds ratio term, right? And on the no term, which was 30%, and by the way, maybe was 20% minus 5% for X entropy, whereas the no term is going to be 30% minus 5% for X entropy, plus, minus as well, let's say 10% for the odds ratio. And so this is going to get us to a total of 20% here. Here it's going to get us to 15%. And here it's going to get us to 60%. They all add up. They should all add up to 100. So I've got a mistake here. This should be 15% as well. Where have I got the mistake? 40, 20, 40. Let's check up here. So my mistake is actually back here earlier. Originally, I was saying I should move with cross-entropy from 40 to 50, and maybe is going down by 15%, and null should still be at 35%. So that was my mistake there. And so that means null was at 40%, and it should be down to 25, and these now add up to 100. But the critical difference you can see here is that with ORPO, you're not just by increasing, in SFT, by increasing the probability of yes, you are reducing, because probabilities have to add to 1, you're reducing the probabilities of all other outcomes. So even if you have a full vocabulary of 100,000 tokens, if you increase the probability of one token, which you will, because the ground truth will have one token as 100% probability, you're going to decrease, somewhat equally all of the other tokens. However, in SFT plus the odds ratio term like ORPO, you're going to do that, but additionally, you're going to have an effect specifically on the yes token, and then a negative effect specifically on the rejected tokens. So it's doing two things. I know I'm repeating myself, but the two things it's doing are, one is it's increasing the ground truth answer, which reduces all other answers, but then it's very specifically dragging up and down the correct answer and dragging down the incorrect answer or the incorrect token. So you can see here the nuanced difference between odds ratio and SFT. Now, in the end, both are somewhat directionally similar, because when you do SFT, you still increase the chosen response and you still decrease the non-chosen responses. It's just that once you introduce odds ratio, it becomes more targeted, because now you're specifically targeting which tokens to reject, essentially. So this was kind of a long way of explaining ORPO, but it's going to be useful because you'll now see how GRPO works. So what GRPO does is it doesn't target things on a pairwise basis. GRPO targets on a group basis. In fact, in DeepSeek, I think they have groups of 8 generated answers. And effectively, it's going to set up the reward for one answer versus a baseline from 7 other answers. So if you have a group of 8, this is a simplified way of thinking of it, but you have a group and you think about the reward versus the reward from the 7 other answers. And this kind of delta, which is the reward minus baseline, this is equal to what can be called the advantage. And this is ultimately what you're trying to maximize in GRPO. So you can think of GRPO as, instead of being pairs, it's like larger groups. It doesn't have to be a fixed size. You could have 8, you could have 12, you could have 16. The larger the group you have, the more VRAM you need for doing the inference on the forward pass. The larger the group you have, the more kind of averaging, the more likely you're going to get a good answer. So probably that helps in some ways. But also the larger group you have, kind of the larger the step you're taking, because you're going to generate many answers and then update on the basis of many answers rather than more kind of incrementally updating the model at each step of GRPO. Now, there's a problem that emerges here, and if anyone has a comment, let me know. But my perception is that one problem with GRPO is that when you generate these 8 answers, say you've 8 answers like this here, it's possible that all of these could be bad. I mean, there's no reason they all have to be good. You can see when I do sampling for data generation, sometimes you do just get all bad answers. And if all answers are bad, there basically isn't going to be much of a reward signal. There'll be no reward signal that's going to help you improve. It's like saying when I prepare my ORPO pairs, I don't just choose random pairs of generated data. I make sure that I only choose pairs where there's one verified and one incorrect. So I'm being very systematic about how I prepare the data. But in reinforcement learning with GRPO, it's not being systematic. It's just generating 8, and it gets whatever 8s it gets. If all 8 of those are bad, the reward for all 8 of those can be bad. Now, I haven't said how is the reward measured. And so let me address that. And there are 2 ways that people are trying to copy DeepSeek. They haven't said exactly DeepSeek how the reward is measured. They've kind of hinted at it. But basically the reward is equal to a sum of an accuracy reward and a format. And the accuracy is just done by numerical comparison, although there's no reason you can't do it with an LLM and a ground truth like I'm doing, or both. And the format is done just by inspecting the using regular expressions of having think tags. So you can see pretty much the reward, the way it's being set up, it's kind of mirroring the way that I'm setting up the data for the ORPO training or for the SFT training. It's just that in GRPO, the way that you effectively choose to assign rewards or values to each of the completions is determined by these rules, whereas the way that I prepare my data set in SFT is determined by those rules. So let me just write that out. So in GRPO, you assign, you do sampling, and then you assign rewards to those samples based on accuracy and format. Then you back propagate based on a reward versus a group of samples and their reward as a baseline. So that's what you do in GRPO. And then in SFT or ORPO with verified rewards, this is really similar because I'm doing sampling, but then I'm only selecting, or this could be called rejection sampling, those samples that meet the criteria of A, accuracy, and B, format, okay? And then do back prop only on the good answers or good, bad pairs. And if you didn't get what I said above, it should be more clear now why you can have this problem if you do the GRPO, because you're blind sampling. You're not applying any restriction or skipping if there are 0 rewards for all pairs. You're doing some sampling. Maybe all 8 samples are bad. Maybe all 8 samples match the format, but maybe your model is already producing the right format. And then you're going to have no reward. You're just going to have 0. In fact, a typical way to do this is just assign 1 point for this reward and then assign 1 point here as well. And so early in the training, your model scores 0 because it's not getting anything right. Then it gets the format and scores 1 out of 2. And then hopefully it starts to score 2 out of 2, ideally. I mean, closer to 2 out of 2 as you start to continue through the training and you get it to actually provide more accurate responses. But yeah, the problem is you can probably pretty easily get to getting the format right. I mean, we can get formats right just by SFT or ORPO as well. But the problem is once you get the format right, you're probably going to have quite a few samples, depending on how hard this task is, that are just all kind of bad. They're all going to score 1, but the model's already scoring 1 because it's getting the format right. And so you're kind of inefficient at that point. Whereas at least with ORPO or SFT, when I'm running the dataset generation separately, I can guarantee that my dataset pairs are all going to be correct pairs, and I'm not going to be doing any backprop where I have kind of poor quality information. Okay, so that was a quick description of GRPO. I'll give a very quick description now of how this kind of emerged from trust policy optimization, which led to PPO, which then led to GRPO. So I suppose to start in the history, you can think about, I mean, there's different ways to roll forward the history here, but you can start by thinking about having cross-entropy as a baseline for training models. And that's typically done on a corpus of, say, web or books. So you have this data. Maybe you're going to filter it, but you're going to use that to just predict the next token. So just predicting the next token. Okay. But then you have some ideas. So idea one is, what if you have some responses and you have humans label which response is better? Okay, that's one idea. And then another idea is, what if you have a model make multiple attempts at a problem where there's a right answer, and you can label which answers are correct and which are bad. Okay, so here you are, and you've got kind of this cross-entropy method for working on a corpus of data. And then you also have this label data. Either it's labeled maybe through verification, or it's verified just by human vibes or by some other method, but you've labeled good and bad responses. And the question is, well, how do you make use of those data sets in order to improve the model? And you know that if you're doing cross-entropy loss, this is quite nice because it means that you're generally going to accurately predict the next token. And it turns out when you do this, you get sentences that kind of complete sensibly because the token distributions match what we actually see in language. Now, the alternative type of loss or reward is you could set up a reward. So the idea here is set up a reward to use for backpropagation that is not cross-entropy, and instead rewards ideas, let's say scores on ideas 1 or 2 above. Okay, so this is your premise. So you're going to set up some kind of a loss function where loss is going to be a function of the human preferences or verified labels, something like this, okay? So broadly speaking, this is what you're trying to do when you're getting to methods like trust region policy optimization. But the problem that you hit, the problem is if you just optimize for this kind of a metric here, so you just purely try to maximize some function or on some set of labels, the problem is you get incoherent responses because your model starts to just optimize for this one label, but it doesn't optimize anymore for readability. So you get incoherent responses because the model doesn't optimize for readability. And it turns out that cross-entropy loss, this does a good job of making responses readable. Let's simplify it to that level. So this is the problem here. And there are 2 solutions. There are probably more, but I'm going to talk about 2. One solution is include cross-entropy loss, which gets readable next tokens. And this is part of the ORPO idea. Okay. The other idea here is to use KL divergence versus a trained model. So what is KL divergence? KL divergence says I have a probability distribution for my trained model of the next token for my trained model, and let's call that A. And B, I'm not going to let the probability distribution of my new model in training depart much from that. That's what KL divergence says. You can imagine a probability distribution of the next token. KL divergence says we're going to keep roughly that shape for the next token. And so this is kind of where you get to trust policy optimization. It basically says, yes, we'll allow for optimizing for labels or some numeric reward. And it says, but we're going to enforce KL divergence so the model stays readable. Okay. So that's the idea of trust region policy optimization. And in order to keep the model close, yes, you can enforce KL divergence, that helps, but you can also constrain the updates that you make in order to optimize for these labels or numeric rewards. So in trying to optimize for this, you can apply some constraints. So there's a further kind of concept here. Limit how far we travel in doing the reward optimization. All right. So yeah, that's why it's called trust region, because you're staying within a certain region where you hope the model stays, to put it kind of in lay terms, the model stays pretty readable. And trust region policy optimization provides a fairly complex method of figuring out what that region is. So you have your model, it's currently here. You don't want it to move too far, but you do want to move towards this reward. And the reward is getting the answers correct and getting the format correct. But you don't want it to move too far. So you need to know what the region is. And there's a complicated formula for getting that. You can decide whether you approximate the region just linearly or quadratically or more complex ways. And trust region policy optimization is one of the more complex ways of doing this. So then proximal policy optimization basically simplifies on TRPO, and TRPO requires, I think it requires Hessians. So it basically requires you to calculate matrices of the cross gradients. And this ends up being fairly complicated and computationally intensive. And PPO shortcuts by basically by using small epsilon changes. It's called clipping. So basically, if there's a big change that's suggested in order to optimize the reward, instead of making that big change, you will clip it. And that clipping will help the model to not go too far out of the region without explicitly calculating what that region exactly looks like. So this is kind of PPO. And GRPO is a further simplification on PPO that makes it more like ORPO. ORPO. Okay. Now, to explain why GRPO is a simplification of PPO, you need to understand the components in PPO. So PPO, it's a lot of things moving at once. You have your original model that you want to optimize. You have some data set or reward function describing what good and bad is. Now, typically, this could itself be a neural network. So you could have a separate neural network, which is called a reward model, to predict the reward. Now, in the case of what we're all talking about here with GRPO and the recent spate of DeepSeek, this reward model is actually not so much a model, but it's an answer checker and a format checker. But most generally, the reward model can be anything. It can be an equation, but it can also be a neural network itself. Now, in addition to having the reward model, which predicts how good a given answer is, you also have what's called a value model. And the value model has the role of estimating what kind of the average reward would be, or what it's a prediction of what the reward is going to be. Now, I know this gets pretty meta, but the reason that it's helpful to predict what the reward would be is it's not enough to know that the model is going to produce a good reward. Let me just give you an example. Say that you're playing a game, a game of basketball where you can score 2 points or 3 points, and you want to just maximize the number of points that you score. It's not enough to know that the reward for a given generation or given completion is going to be 2. because maybe the model is already generating 2 before you do any back propagation. So if the model's already scoring 2 and you do back propagation and it's still scoring 2, that's not an improvement. So what you actually need to know is, what's the reward on this generation? Hopefully it's 3. And the predicted reward before that back propagation is just 2. Now you can say, okay, this improvement is actually doing 3 minus 2. So I'm actually getting an improvement. So what I'm saying is, you kind of need to know what the baseline performance of the model is. What's the baseline performance you predict, as well as knowing what the improvement is, because then you can calculate a delta. And actually, this is what these methods are all based on. They're based on this thing called advantage, which is equal to reward minus value, which is really another way of saying the outcome minus, well, it's really the kind of improved outcome minus the baseline outcome. Okay, so this is pretty annoying with PPO and TRPO as well. This is annoying because you need to have a base model you're training. You need to have a reward model or an equation. Plus you need to have a value model. Which, I mean, in principle, it could kind of be an equation, but typically this is going to be some kind of a neural network. And this is just a lot of stuff to manage. This means you need to have a lot of VRAM, a lot of things to manage, a lot of VRAM, a lot of steps, right? That's, yeah. And so what GRPO says is, let's drop the value model, which is our kind of prediction of baseline performance. And instead, let's estimate the baseline by sampling and averaging. And we'll sample a group of answers, which is why it's called GRPO. Okay, I'm getting some autocomplete here, but this is true. Do sampling, assign rewards to those samples based on accuracy and format, and then back propagate based on a reward versus a group of samples, and a reward is the baseline. So I've clearly given it enough above for it to autocomplete correctly. This is roughly what's happening in GRPO, and you can see it's rewarding based on a group rather than pairs like ORPO. Now, is that really different? Because keep in mind, in ORPO, even though you're using pairs, you're going to have a batch of pairs. So when you have a batch of pairs, that's, it's not that dissimilar to optimizing versus a group. In fact, it would be even more equivalent if you create ORPO pairs in a complete format. See my first video for that, where every correct answer gets paired with all of the incorrect answers within a mini batch. That would make it even more equivalent to GRPO. Now, the formula for the back propagation and the calculation of the odds, that's not exactly the same. The way that you're attributing the reward to each of the tokens, it's not exactly the same within GRPO and ORPO, and it's not exactly the same, again, in cross-entropy loss. But directionally, these are all doing the same things, which are trying to increase the probability of correct answers, which naturally decreases the probability of bad answers, but actually explicitly reduces the probability of bad answers if you're doing GRPO or ORPO versus SFT or cross-entropy, where you're only explicitly increasing the good answers, and indirectly then, because probability equals 1, you're decreasing the incorrect answers, but you're also just decreasing all of the other kind of random answers which are badly formulated or badly formatted, which, by the way, may not be a bad thing. So that's why it's not entirely clear to me that you get a huge benefit going beyond cross-entropy loss. Okay, final remarks. What is the magic in doing GRPO? So the main part of the magic is the sampling plus reward, which acts as a verifier. And by the way, the reward method, if we're just checking correctness, the reward is actually, it's discrete. It's quantized. It's not continuous. I think there's this kind of perception that maybe it's better doing ORL or GRPO because it's a continuous reward. And often the rewards are continuous if the reward model is a neural net. But it's not continuous here because we're actually using comparisons and binary comparisons on format and accuracy. So it's not like we have a continuous reward that's somehow giving us this benefit. No, the benefit is coming from the fact that we're using verified rewards. And this really isn't different than just categorizing your data, as I said. So I'm repeating myself, but this I think is a key point that's maybe not entirely understood. I think another misperception is that somehow if you use a neural net because it's continuous, if you use a neural net as your reward function instead of an equation, it's going to be somehow better than using just an equation or using some labeled data directly. But the neural net that is the reward, that ultimately has to be trained on some data. So it's questionable as to whether that model itself can be better than just the right equations to directly handle the labeled data itself. So it's not entirely obvious that you get a benefit just by introducing a neural network as a reward model. That's kind of the key insight actually of DPO and of ORPO, which is that, well, we were training these reward models off of labeled data. Why were we even bothering? Why don't we just more properly incorporate the labeled data into a loss function and directly use that to train the model? That's the key insight of DPO, which is direct preference optimization, and it's very similar to odds ratio preference optimization. Okay, so that is the main magic of GRPO. And then there's a nuanced and kind of less unclear point here, which is, one, is it really that different to backprop on correct answers versus correct, incorrect pairs or groups? That's like the fundamental question of, is cross-entropy loss any better or worse than doing something like ORPO or than doing something like GRPO? Okay, so that was my big overview of GRPO.